600 kilometers per hour, 373 miles per hour. A train that touches nothing. It has no wheels. It does not roll. It floats on 10 millimeters of empty air, the width of a pencil, and it moves faster than a Formula One car at full throttle, faster than a jet on final approach. And underneath it, the ground it was built on is sinking. Shanghai sits on river mud, soft alluvial clay laid down by the Yangtze over 10,000 years, wet and unstable to a depth of dozens of meters. Every heavy structure the city builds slowly drowns in it. Skyscrapers settle, roads crack. The earth here does not hold. It swallows. China built a train that flies over it anyway. $1.33 billion. 2.5 years. A guideway laid to a tolerance measured in millimeters across 30 kilometers of sinking delta. The first commercial high-speed maglev on Earth, and then a second machine, faster, that pushes the whole idea to 600 kilometers an hour. This is how you build a train that never touches the ground, on ground that will not stay still.
Ensuring the structural integrity of these massive beams is our primary engineering challenge on this site.
The first problem, the ground. Start with the enemy nobody sees. The ground. A normal railway sits on ballast, crushed stone that spreads the load, and can be re-leveled by a work crew with a tamping machine. If the track sags a centimeter, you lift it, pack more stone underneath, move on. Forgiving. Cheap. Slow. A maglev guideway cannot be forgiving. The train floats on a gap of 10 millimeters. If the guideway drops by even a few millimeters in the wrong place, the gap changes. And if the gap changes while the train is passing at 431 kilometers an hour, the machine touches steel. At that speed, touching steel is not a bump, it is a catastrophe. So the guideway has to hold its shape to within millimeters, and it has to hold that shape on top of Shanghai's river delta, which is doing the opposite of holding still. And Shanghai does not just have soft ground, it has ground that has been sinking for a century. Decades of pumping groundwater out from under the city had drained the soil and let the whole metropolis settle, in places by more than 2 meters over the years. This is a city that has watched its own streets go down. Building the world's most precise track on top of the world's least patient ground was the contradiction the engineers had to solve before anything could float at all. The original German design assumed firm European ground. One support column every 50 meters. Chinese engineers took one look at the alluvial soil east of the city and cut that number in half. One column every 25 meters. Twice the supports, twice the foundations, twice the work, and the ground was never trusted to stay put. The columns were monitored for settlement, measured and remeasured, because on this soil finished is not a permanent state. A guideway laid perfectly today can drift out of alignment as the earth beneath one pier gives way by millimeters next year. The maintenance never ends. The delta never stops pulling down, and each column could not simply sit on the mud. Each one is anchored on concrete piles driven down as deep as 70 meters. The height of a 20-story building pushed straight down into the earth, searching for something solid to stand on. Here is the escalation that kept the engineers awake. If one column settles a few millimeters, the guideway above it bends. If the guideway bends, the levitation gap changes. If the gap changes at full speed, the train no longer floats level. One column out of hundreds starts the failure.
We utilize a specialized concrete pouring technique for these pillars, allowing us to accelerate the construction of the elevated track significantly.
So before a single magnet was switched on, China had already fought and won the first battle, against the ground itself. The mud becomes a foundation. The foundation becomes a column. The column becomes a road for a train that will never touch it. Step 1. Manufacturing the impossible track. Now the guideway. And this is where the numbers stop being ordinary. You cannot pour a maglev guideway like a highway. It carries the magnets, the guidance, the power, and the geometry that keeps a floating train alive. Every beam has to be shaped to a precision that ordinary construction never has to reach. fractions of a millimeter over a beam tens of meters long. China did not truck these beams in from a distant factory over bumpy roads that could warp them. It built a climate-controlled manufacturing hall over a mile long, running right alongside the route, temperature-controlled. Because concrete expands in heat and contracts in cold, and at these tolerances, a few degrees of temperature swing is enough to push a beam out of spec. Think about that. A factory a mile long, built to make one thing, then torn down when the job was done. The beam is cast, cured, measured, ground, measured again, and only then carried out and lifted onto the columns.
They built a mile-long factory just to make the track, tritium, harder than the train.
Then the beams go up, each one aligned to its neighbors, so the seam between them is nearly invisible to the train's magnets flying past at 120 meters every second. A misaligned joint is not a rough patch. It is a place where the floating gap suddenly narrows, and there is no room to narrow. The gap is 10 millimeters. 10. There is no margin. None. Step 2. Making metal float. Now the part that sounds like science fiction and is actually a fight the machine has to win thousands of times every second. The Shanghai Maglev uses electromagnetic suspension. Electromagnets on the underside of the train wrap up and around the edges of the guideway and pull the train up toward the rail from below. The magnets pull the train up, not push, pull. The train hangs off the track, wrapped around it, lifted by attraction toward the steel above. And here is the problem with magnetic attraction. It is unstable. The closer the magnet gets to the steel, the stronger the pull becomes. So if the train drifts up even slightly, the pull increases, and it drifts up more, and it slams into the guideway. And if it drifts down, the pull weakens and it falls. There is no natural balance point. Left alone, the system destroys itself in a fraction of a second. So the train does not leave it alone. Sensors measure the gap thousands of times per second. A control system adjusts the current in the magnets thousands of times per second. Too much pull, ease off. Too little, push harder. Constantly. Relentlessly. The 10-millimeter gap is not a resting state. It is a decision the machine makes over and over, faster than any human could ever react, for the entire length of the journey. Cut the power for real, and the electromagnets die. But the designers planned for that too. Onboard batteries hold the levitation alive long enough to glide the train down safely onto skids. The train is never allowed to simply drop. Escalation, again. A sensor lies about the gap. The controller trusts it. It feeds the wrong current. The gap collapses. At 431 km/h, the gap collapsing is the train touching the rail. One bad reading starts the failure, so every reading is checked, mirrored, and voted on by redundant systems before the magnets ever move. Step 3. Pushing it forward without touching it. The train floats. Now it has to move. And it cannot push against anything because it touches nothing. So the guideway itself becomes the engine. Buried along the track is a long series of electric coils, a motor turned inside out and stretched across 30 kilometers of concrete. Run a moving electric current through those coils, and you create a magnetic wave that travels down the track. The train's magnets lock onto that wave and are dragged along by it like a surfer carried by a wave that never breaks. The train has no engine of its own. The track is the engine. Power only flows into the section of track where the train actually is. The wave moves ahead of the train, and the train chases it forever. That is why it accelerates the way it does. From a standstill to 300 kilometers an hour in 2 minutes and 15 seconds. No wheels to spin, no friction to overcome except the air. The push is clean, silent, and enormous, and it works in reverse. To stop, you run the wave backwards. The same motor that flung the train forward now drags against it and brakes it, turning motion back into electricity. The track speeds the train up. The track slows it down. The track is doing everything the train cannot. But a motor stretched across 30 kilometers cannot be powered all at once. That would waste enormous energy energizing empty track. So the guideway is cut into sections, and power is switched into each section only as the train arrives, then switched off behind it, a moving pool of energy chasing the machine down the line. The handoff between sections has to be seamless. If the current in the next section arrives even slightly out of step with the train, the smooth pull stutters, a jolt in a machine that is not supposed to have any. At 431 kilometers an hour, the switching between sections happens in a blur. Dozens of times, every one of them timed, to the position of a train that is covering the length of a football field every single second. The train chases power down the track. The power is never everywhere along the line. It is only ever exactly where the train is, and it moves on the instant the train does. Step 4. Holding the line sideways. Lifting the train is only half the fight. Something also has to keep it centered, left and right, over a rail it never touches. At 431 kilometers an hour, the train is a light body moving through a river of air. A gust of crosswind hits the flank and tries to shove the whole machine sideways off the guideway. A curve tries to fling it outward. Nothing is holding it in place mechanically, no wheels pressed against no rail. If the train wanders sideways by centimeters, the magnets on one side jam toward the steel, and the ones on the other pull away into nothing. So, a second set of magnets works only on the sides. Guidance magnets, gripping the edges of the guideway laterally, pulling the train back to center the instant it drifts. Same unstable physics. Same relentless correction, thousands of times a second. The train is not sitting on the track. It is suspended inside a cage of magnetic force, held up, held in, held straight, all at once, all by fields of attraction that would collapse the moment the control system blinked. And the wind never stops testing it. Out over the open delta east of Shanghai, there are no hills, no forests, nothing to break the gusts coming off the sea. The guideway carries the train straight into them. A crosswind that a normal train would shrug off can move this one, and the magnets catch it and correct it before a passenger ever feels a thing. Escalation, one more time. The wind pushes the train off-center. The guidance magnets on the far side lose their grip on the steel. Their pull weakens. The train drifts further. If the correction is a fraction of a second too slow, the drift becomes contact. The wind starts the failure, so the system answers it faster than the wind can change. Engineering Deep Dive 1, the wall of air. Here is why 600 kilometers an hour is a different universe from 300. Air resistance does not grow in a straight line with speed. It grows with the square of speed. Double your speed, and the air fights you 4 times as hard. Push from 300 to 600, and the wall of air in front of the train becomes overwhelming, the single biggest thing standing between the machine and its top speed. At 600 kilometers per hour, the overwhelming majority of the train's energy is not spent moving the train. It is spent shoving air out of the way. This is the enemy that never tires. The ground you can pile onto. The magnets you can control. The air you can only shape yourself against, which is why the 600 km/h machine is drawn out into a long, low, knife-edged nose sculpted in a wind tunnel to slice the air instead of hitting it. The number, 600 km an hour, 373 miles an hour, Beijing to Shanghai, over 1,000 kilometers, in 3.5 hours, city center to city center, without ever leaving the ground and without ever touching it. Engineering Deep Dive 2. The 10 mm problem. Return to that gap, because everything lives or dies on it. 10 mm. Less than the thickness of your finger. That is the entire distance between a train carrying hundreds of people and the steel it is wrapped around, at speeds where a car would be torn apart. Why not make the gap bigger? Safer, surely, to float higher off the rail, because the strength of a magnet drops off brutally with distance. Pull back to a larger gap and you lose most of your lifting force. You would need magnets so heavy and so power-hungry that the train could no longer carry its own suspension. The physics forces the engineers into the tightest, most dangerous-sounding number, and then demands they hold it perfectly. So the ride you feel, smooth, silent, floating, is not calm at all underneath. It is a machine holding a 10mm line at 5 times highway speed, over sinking ground, correcting itself thousands of times a second, every second, for the entire trip. Smoothness, here, is the visible face of violence perfectly controlled. The Kyle reveal. Step back and look at the whole thing. The Shanghai line runs 30 kilometers, from a metro station on the edge of the city out to the international airport. 8 minutes and 10 seconds end to end. In those 8 minutes, the train hits 431 kilometers an hour, holds it for a matter of seconds, and slows down again. It is less a journey than a demonstration. Proof, laid in concrete, that the impossible train is real. Now scale the idea up. The 600 km/h machine unveiled in Qingdao in 2021 is not a 30-kilometer showpiece. It is meant for the gaps that airplanes fill today. Hundreds of kilometers, city to city, closing the distance between high-speed rail at 350 and a passenger jet at 900. 2 to 10 carriages, each holding more than 100 people. A jet's speed on the ground, gliding on air. Put the numbers side by side. A car on the highway, 120 kilometers an hour. A conventional Chinese bullet train, the fastest wheeled trains in regular service anywhere, 350. The Shanghai Maglev, 431. The Qingdao machine, 600. Each step up is not a small improvement. Each one is a leap into a harder fight with the air, the ground, and the gap. A fight that most of the world's railways never even attempt. You would ride it and feel almost nothing. A faint push in your seat. The world outside blurring into color. And you would have no idea that beneath you a machine is fighting the ground, the magnets, and a wall of air all at once, and winning 10 millimeters at a time. The resistance montage. And still, the story is not clean. The Shanghai line was supposed to be the beginning. A maglev to Hangzhou. A maglev network stretching across the country. It never came. The technology was foreign. Licensed from Germany's Transrapid, and expensive, far more per kilometer than conventional high-speed rail. Critics called the Shanghai line a train to nowhere. 30 kilometers that stopped at the city's edge instead of reaching downtown, so travelers still had to change to the metro to finish the trip. The extension plans met public worries over radiation and noise from residents along the route. Budgets were questioned. Politics shifted. Conventional high-speed rail, cheaper, wheeled, good enough at 350 km/h, spread across China by the tens of thousands of kilometers instead. A licensing dispute, a cost fight, a route that fell short of downtown, neighborhood protests, a rival technology that was simply cheaper. And still, in Qingdao, the 600 km/h machine rolled out of the factory anyway. The hidden cost. Here is the part the speed records never mention. The world's first high-speed maglev, the one that proved it could be done, runs 30 kilometers and stops short of the city it serves. $1. 33 billion, nearly $40 million per kilometer, for a line that most Shanghai residents will use once as a novelty on the way to the airport. The fastest commercial train on the planet became, in practice, a very expensive shuttle. The 600 km/h successor is faster than anything on rails. But years after its unveiling, there is still no long line for it to run on. A maglev cannot use ordinary high-speed track. It needs its own dedicated, precision guideway, built from scratch, at maglev prices, over whatever ground lies in the way. To go 600 km/h from Beijing to Shanghai, someone first has to build over 1,000 kilometers of that guideway. It has not been built, so the machine that touches nothing is held back by the most ordinary thing of all, the cost of the ground it would need to fly over. And there is a quieter cost, too. The Shanghai line has to be watched forever. The guideway that floats a train on 10 millimeters cannot be allowed to drift, and it sits on soil that drifts by nature. So crews measure, adjust, and realign year after year, holding a millimeter tolerance against a delta that never agreed to hold still. The train that needs no wheels and no rails to touch still needs an army of people keeping its road perfect. A floating train is not a train that runs itself. It is a train that demands perfection from everything around it, every day, or it does not fly. The train floats, the economics do not. The dark twist plus ending. We tell this as a story of speed. 431, 501 on a test run, 600 on the machine in Qingdao. But speed was never the hard part. China solved speed decades ago. The hard part was everything speed asks of the ground beneath it. A gap of 10 millimeters over soil that sinks. A guideway held to fractions of a millimeter across 30 kilometers of river mud. A motor stretched into the track itself. A wall of air that grows faster than the train can. Every one of those was beaten. And the thing that stopped the Maglev in the end was not physics at all. It was the bill. Not a train to nowhere. A train ahead of everywhere, built perfectly, for a country that chose cheaper wheels instead. China did not fail to build the impossible train. China built it twice, and then discovered the impossible part was never the floating. The train still floats, on 10 millimeters of air, over ground that keeps on sinking, waiting for a line long enough to let it run. For now,